Assalamu alaikum. Bismillah ar-Rahman ar-Rahim. Welcome to a new lecture series on science, Islam and science. And the title of this lecture series is Fine-Tuning of the Universe. And I am truly excited about this series because in talking to Muslim young people, youth and young adults, they tell me that the material here, bar none, has been of significant importance to them in their faith, that it has presented in their minds the most convincing set of arguments for the existence of God, particularly in the face of a culture which continues to tell them that science has done away with the God hypothesis. And so, if you know something about fine-tuning, you already know the importance of this material from a theological perspective. And if you don't know very much about it, I hope that you will tune in for this series and that at the end, inshallah, you will be convinced that this is indeed important material. It is recent material. It is only a set of discoveries which has been expanding for about 50 years. So it is recent material which really has redefined and reshaped the dialogue of religion and science. And indeed, it has, I believe, entirely turned the tables on those proponents of scientific materialism who say that science has no need for the notion of God. And it is a very strong set of supporting arguments and convincing discoveries, bolstering the notion of scientists who are also people of faith, who not only see no conflict between science and religion, but indeed see a harmony between the two. So with that, let's begin talking about fine-tuning. And if we're going to begin, let us begin at the beginning. And that beginning is, of course, the Big Bang. Everyone has heard of the Big Bang. This was just a theory in the 1950s based on the conclusions that came out of Einstein's general theory of relativity. And initially, it was really not accepted by the vast majority of scientists, but certainly in the past few decades now, there's almost unanimous acceptance and many, many pieces of very convincing evidence that the universe indeed started in a Big Bang. And you see here Stephen Hawking's quote from The Universe in a Nutshell, where he said, Roger Penrose and I, and for those of you who follow science news, you know that Roger Penrose was recently awarded the Nobel Prize in Physics for his work in general relativity. Roger Penrose and I were able to show that Einstein's general theory of relativity implied that the universe and time itself must have had a beginning in a tremendous explosion, and that is what is now known as the Big Bang. So somehow this Big Bang had to produce the complex set of arrangements, the special arrangements, which allowed stars, galaxies, planets, biospheres, and life to form. So how did that happen? Well, scientists, physicists, chemists, astrophysicists, biologists, astrobiologists, of course, have realized that for life to occur in the universe, somehow this tremendous explosion of the Big Bang must have produced complex chemistry, long-lived stable stars, multiple chemical elements, including heavy elements and carbon and oxygen. Life depends on about 20 or so elements in the periodic table. And the ability of these chemical elements to form bonds and interact, and so give rise to and continue life. So how do we understand how this happened? Well, scientists try to do that by working to discover the laws of nature. The various laws of physics and chemistry and biology that allow us to understand how particles interact, how physical systems evolve. And as you know, these laws of nature are encapsulated as some sort of a physical law, like Newton's law of gravitation, like Einstein's special and general theories of relativity, like Maxwell's equations of electromagnetism, like the equations and theories of quantum mechanics, quantum field theory, and so forth. These are all laws that again tell us how do particles interact, how physical systems evolve. And each of these laws has a certain form, perhaps a mathematical equation. And that form might describe one of the forces of nature, like the force of gravitation or electromagnetism or the strong nuclear force or the weak nuclear force. And within each of these laws, there will be constants of nature, so that scientists discover a certain equation that seems to describe a facet of nature, like gravitation. But within those laws are constants that are outside the laws. They are not something that we can deduce, but they are properties of the universe that go into the laws. For example, if you put two 1 kilogram masses 1 meter apart, there will be a certain force of gravitation between them. The strength of that force can be described by a law of nature, but it involves a constant of nature, which is the gravitational constant. Why is it that two 1 kilogram masses 1 meter apart attract each other with this much force, but not more or less? Because the universe has a certain gravitational constant that dictates that strength. And these constants of nature have to be measured. They are properties of the universe woven into its fabric. They are nothing that we either assign or deduce through thinking or logic or mathematics. So examples of that are the masses of fundamental particles, strengths of fundamental forces, and so forth. Now, after we've specified all that, there are also initial conditions. For example, I said two 1 kilogram masses 1 meter apart. Well, those are initial conditions. They could have been 2 kilogram masses, or they could have been 10 meters apart. So to understand or apply a physical law, we also have to look at the initial conditions in which that law is working. So let's take Newton's law of gravitation. If we have mass 1 and mass 2, a distance d apart, the force of gravity between them is described by this simple law, which is mass 1 times mass 2 over the distance squared times g, the universal gravitational constant. And you can think of mass 1, mass 2, and d, for example, as initial conditions, and g as a constant of nature. And here's the law. And when we apply the law, we then get the force of gravity. And so this can be applied to a system like the Earth and the Sun. And we can understand how much gravitational pull the Sun exerts on the Earth by using Newton's law of universal gravitation, putting in the gravitational constant, which again, I remind you, is woven into the fabric of the universe. This is not something that we make up. This is something that we measure. That if you have mass 1 and mass 2, to figure out how strongly they attract each other, we use this property of the universe in this equation, and then we will get the force of gravity. And so we can put in the distance between the Earth and the Sun in meters, the mass of the Earth, the mass of the Sun, the universal gravitational constant, and we get the force of gravity that the Sun exerts upon the Earth. And of course, the Earth exerts the reciprocal force on the Sun. And this force makes the Earth orbit the Sun, or really keeps the Earth in orbit around the Sun. So we have constants of nature like G and initial conditions like R, the distance between the Earth and the Sun. So for 2,000 years, scientists have been very busy discovering the many complex laws of nature that now make up physics. Laws of gravitation, laws of electricity, laws of magnetism, then a synthesis that synthesized electricity and magnetism, special relativity, general relativity, which revamped Newton's laws of gravitation, the standard model of particle physics that rules the quantum world, coupled with quantum mechanics. Then quantum mechanics had to be reconciled with special relativity through the work of Paul Dirac. And then quantum field theory had to be developed. So scientists really have been making tremendous advances, and for 2,000 years have been busy discovering the laws of nature and measuring the constants that go into these laws, the universal constants. But it's only been very recently, in the last 50 years, that somebody asked the question, well, what would happen if the universal constants were just a little bit different? Yes, we have this measured value of G. What if G were a little bit different? What if it were a little bigger? Well, nobody thought much of that. Well, the apple would have probably fallen a little bit faster on Newton's head, and that's it, because the strength of gravitation would be a little bit more. And this is, of course, from the apocryphal story that Newton was sitting one day beneath an apple tree, an apple fell on his head, and that led to his contemplation of, why is it that gravity does this and how does it do it and so forth. And these are many of the other constants. Here's the Newtonian constant of gravitation. Here's the speed of light. Here is, for example, Planck's constant, which underlies all of quantization and quantum mechanics. Here's the elementary charge on an electron or proton. Again, we don't assign these. The universe tells us, and we measure that an electron or a proton has 1.602 times 10 to the 19th coulombs of charge. We have the mass of the electron, the mass of the proton. We have the fine structure constant that governs the strength of electromagnetic forces, and so forth. So we have a whole bunch of constants that enter the laws of physics. We don't measure these constants. We don't deduce these constants, we measure them. They are part of the fabric of the universe. And it is only very recently that scientists have started asking the question, what would be the implications if G were different, if the mass of the electron were different, the mass of the proton, the fine structure constant, Rydberg's constant, and what implications would that have for the universe as a whole? And this is now where we get to what fine-tuning is. What fine-tuning is the discovery, the surprising discovery, the amazing discovery, the revolutionary discovery that, as summarized here by Luke Barnes, who is an astrophysicist, that even the smallest changes to the laws of physics as we know them tend to make a universe which is completely unlivable. This is called the fine-tuning of the universe and is frankly one of the most baffling facts in all of science. So this is what fine-tuning is. It was the sort of surprise set of discoveries over the last 50 years that even the tiniest changes in any of these constants of nature would completely destroy the fabric of the universe. Now, why is this important? Because if we say that the universe arose in a haphazard fashion and that life is a matter of chance, one would expect a very wide set of tolerances for life to arise. That it wouldn't matter very much what the charge on the electron or proton is. It wouldn't matter very much what Planck's constant is. It wouldn't matter very much what the gravitational constant is beyond some subtle alterations, like the force of gravity would be a little bit stronger, the way it is, for example, stronger on Earth than on the moon. Or the electrostatic charge would be a little bit more, and so static electricity would shock you more, and so forth. It was a complete surprise that life has almost no tolerance for any change to these constants, that these constants have to essentially be exactly what they are. Otherwise, the universe could not produce anything resembling life. And of course, the theological implications of that are quite straightforward. And so here again, Luke Barnes is saying that since physicists have not discovered a deep underlying reason for why these constants are what they are, we might ask a seemingly simple question: what if they were different? What would happen in a hypothetical universe in which these constants had other values? Now, mathematically, because we have laws of nature, we can use the same laws of physics, but with these different constants, and see what would happen to stars, what would happen to chemistry, and so forth. And as Luke Barnes said, there's nothing mathematically wrong with these hypothetical universes, but there's one thing that they almost always lack: life, or indeed anything remotely resembling life. There would be no chemical bonds, no chemistry, and of course, no DNA, no planets, no rocks, no water, etc., etc., etc. And that the constants are all arranged in what is, mathematically speaking, the very improbable combination that makes our grand, complex, life-bearing universe possible, is what physicists mean when they talk about the fine-tuning of the universe. So really, he has defined it very, very well for us. And of course, this now, as you can see, would become very significant in the discussion or the debate between scientific materialism and scientific theism, because it would be very, very odd for a universe to arise by chance in a haphazard fashion, and life to arise as an accident, yet it turns out that all of the fundamental constants of nature need to be exactly what they are for life to arise. And this is not just the opinion of Luke Barnes. This has now become a pretty straightforward scientific understanding, but really has yet to filter to a lot of the public discourse. But you see, for example, Stephen Hawking, who is well known to have been an atheist. He says the remarkable fact is that the values of these numbers seem to have been very finely adjusted to make possible the development of life. John Gribben, a very well-known science writer, says if we modify the value of one of the fundamental constants, something invariably goes wrong. So for example, we adjust the mass of the proton. And we think, okay, well, let's go ahead and adjust the mass of the electron and the electric charge to fix it. He says when we adjust a second constant in an attempt to fix the problems that result from adjusting the first constant, the result generally is to create 3 new problems for every one that we fix. The conditions in our universe really do seem to be uniquely suitable for life forms like ourselves, and perhaps even for any form of organic chemistry. And Paul Davies, a very, very famous physicist and well-known author, says the cliche that life is balanced on a knife edge is a staggering understatement in this case. No knife in the universe could have an edge that fine. And so I hope that 2 points are clear. Number one, this is not some theory or idea concocted by religious people to have science bolster religion. These are hard-edged scientific discoveries that really have nothing or had nothing to do with religion or the debate about God or the God hypothesis or intelligent design. But of course, when this series of facts was discovered, it immediately had stunning implications for the discussion of religion and science. And while I have heard fine-tuning discussed in other religious communities, to be honest with you, I have not heard it discussed in the Muslim community. I have not heard detailed discussions of it. And I thought that this would be something very important for our community to learn about, and that this is a discourse that we need to be part of. And so I hope that this has intrigued you and that you will tune in now to the second part of the introduction. We will have another introduction part 2, and then inshallah we will launch right into trying to understand something about fine-tuning. So salamu alaikum, and I hope inshallah you will tune in for the next lecture. Take care and God bless.